We also have to specify the algorithms, basically explain what they do, kind of like in mathematical notation, what they do. That's also really important because distributed systems with a small difference in specification, maybe the code is totally different. They're already between asynchronous and synchronous. We just add one letter in front of the word synchronous, put an A, maybe the whole thing becomes impossible. Okay? Just one letter difference. Okay? So the specification is, so there's an interface, so that's the messages going in and out, what we can call the API, Application Programming Interface Contract. Then we have the properties of what the algorithm is doing, which are safety and liveness. We have the model. So timing, is it synchronous or asynchronous? What kind of failures do we have? Do we have crash failures or Byzantine failures? It's very important. Algorithm is totally different if we have different kinds of failures. Okay? We're totally different between synchronous, asynchronous, partially synchronous. It's really important. Okay? So this is all super important because we're going to be writing very complicated algorithms. Okay? I don't want to scare you away, but just to say that we have to be very precise, because if you're not precise, you get totally messed up. As long as you follow this, everything will be fine. Okay? And then, of course, there's the implementation. So this implementation is this pseudocode, huh? But we also have to talk about this part, which is how do we say what is the algorithm doing, okay? What does reliable broadcast really mean? When I say all or none, what does it mean exactly? What failures am I allowing? Is it asynchronous or synchronous? That's really important, huh? Remember, some things are very easy when it's synchronous and they're impossible when it's asynchronous. So this is really important. We have to understand the model. Huh? So all that's part of the specification. Okay, and then we start writing code. But let me make a break now. I think that's enough stuff before the break. Let me talk about specifying systems now. So the implementation is going to use this event-based pseudocode where we have these boxes. Each of the boxes is running like sequential code, and messages can come in and come out, and they're connected like a stack. So that's the implementation. But the specification, there's three parts. There's the API, so basically the requests and responses, the calls. But also there's the properties, the formal properties of the algorithm. What exactly is it doing? And then there's the model it runs on. For a distributed system, this third part is really important. Usually people tend to forget the model on non-distributed systems. They sort of forget what it's running on. But for a distributed algorithm, this is critical. Because sometimes it's the difference between maybe efficient algorithm or impossible algorithm. So failures, is it crashed up or Byzantine or something else? Timing, is it synchronous or asynchronous? Okay, or partially synchronous. Makes a huge difference in the code. So it's not just the properties, but it's the model. It's very important. Okay, so that's the idea. We're going to show you examples. So here's a simple example. Start really simple. This is actually coming from the book by Garraway and Rodriguez. So this is a printing module. So there's one request and one confirmation, which is an indication. So the print request is a message going in there saying, I want to print str, which is a string, and I have given it some ID, some number that identifies it. And then I get a confirmation message back later telling me that the printing request with this ID has printed successfully. So that's a very simple interface, okay? And here's the code. This is our very, very simple first code. It has only one little yellow box here. Upon event, print request, request ID string. It does print. Yeah, so we're assuming that there's some basic print functionality. Yeah? So we're actually just putting it inside the yellow box, print the string, and then trigger, which is sending a message back. Print confirm with the same request ID. See, so it's receiving a message, print request, it's doing the print, and it's sending the confirm. Very simple. It's our first piece of pseudocode. Okay? So here's a more sophisticated one. So this one is called bounded print. So it's very similar, except that the printer has only a certain number of lines that you can print, and then it runs out of paper. Okay? So you have bounded print request, again with ID in a string. You get the confirmation message, request ID back, print status, and the status can be either okay or not okay. Not okay. So you can only do a certain number of prints, and then it runs out of paper and it says no. And then there's another one, an indication called print alarm, which is independent of that. As soon as you run out of paper, it immediately sends the message print alarm. Okay? So basically it's a printer with a limited number of lines that it can print. So here's the code. Now we have 3 yellow boxes here because we have 3 events. We have the bounded print request, but this module is going to use the other one. Okay? So in fact we can see it as an example of this code. So the first module that we saw here, this one is called print, okay? And this one is called bounded print. So we can actually look at it like this. We have a module called print, and we have a module called bounded print. Okay, so we have bounded print request, which comes in here. But this module uses the print module, so it sends a print request. It'll send a print request to print. It will receive print confirm from print, and it will send print status back. Okay? So if you get a print confirm from the bottom print module, then you know everything is okay, and it sends print status okay. But if I do bounded print request, okay, and the bound is equal to 0, so there's some local variable here called bound. If it's equal to 0, I immediately send a message back, print status not okay. Okay? So there's 2 ways that the print status message can be sent. If the bound is bigger than 0, it decrements. Bound is bound minus 1. It sends print request down, okay, to the print module. But if the bound is 0, if the bound has become 0, then we're done. There's no more print possible. So it sends a print alarm message back. Yeah. Print alarm can go back. So, but in this case, it's still allowed to print. But print alarm means that there's no more print allowed after. Okay? So if there's another bound print request coming in after that, bound would be equal to 0 and it will do not okay. You see, so each of these yellow boxes has some pseudocode, which is standard imperative language. So there's local variables that you can assign. There's a special message called init. When the system starts up, when it starts up, a single init message is automatically sent to each yellow component, allowing it to initialize its local variables. So this is a new thing here in this model. Huh? So the init is automatically generated when the component is created, when the system starts up, once only, to initialize the local variables, or do whatever computation that's needed in the beginning. Okay? So you see there's 3 little yellow boxes inside of this bounded printer. And each one of them handles a different event. There's the init one. Bounded print request handles a request, and print confirm handles the indication, the confirmation coming back. So there's 2 messages can come in here. So this middle one is handling a message coming from higher up, and this one, bottom one, is handling a message coming from below. Print confirm is coming from the print module underneath that. So this is a system with two components. Very simple. It's just an example to show you how the whole thing works. Okay? So you see how it works? It's okay? It's reasonable? And all the algorithms are going to be written like this way. All of the algorithms in the course. So that's an example of implementation. But now we're going to talk about specification. Now I want to talk about correctness. How do you define the properties of your program? I said that reliable broadcast is all or never, all or none. What does that really mean? I need to be very precise. So I'm going to write it in terms of predicates, formulas that are true or false. And there's two kinds of properties in a program. So we have to talk about the fundamentally two properties of any program, which are called safety properties and liveness properties. So I don't know if you've already seen formal definition of these guys. Have you seen it? Who has already seen this formal definition? Some of you? A few? Okay, others have not? We will see a formal definition here. So this formal definition should, maybe it's not exactly the same, but it should be exactly the same idea as the one you've seen. So I also will give intuition on this. So a safety property, the intuition is that bad things never happen. And liveness properties is that good things will eventually happen. So the safety property, like if you're driving a car, the safety property means you will not have an accident, for example. That's a bad thing. And the liveness property says you will actually reach your destination. That's not a good thing. You will reach the destination. So you need both. So I'm going to start by giving some intuitions. So here's the properties of you in this course. Okay. So the safety property is that you should not fail the exam. You should never fail the exam in this course. Okay. Failing the exam is very bad, so it should never happen. But the liveness property is that you should take the exam. It's very easy to have the safety property by itself. If you never take the exam, then you will not fail, right? So it's very easy to have one of these two. The real hard part is to have both. So it's easy to not fail, just never take. Or it's easy to take the exam. You just show up during the exam and you write random doodles on the paper. You have taken the exam. The real trick is both together. Okay? So safety and liveness together determine what the algorithms will do. So here's another example. Traffic lights. So you have cars coming to an intersection. You have green, red lights. So the safety property for the lights are more than one direction should never have a green light at the same time. I mean, if I had green lights, orthogonal directions. So direction. So this is okay. Two different directions should not have green lights at the same time. Well, that's easy to satisfy this. Just make all the lights red all the time. It's very easy. But no cars can move, so that's not enough. So you need liveness property. Every direction should eventually get a green light. Okay? Eventually the light should turn green for every direction. Eventually means after finite time. Okay? So again, it's very easy to have liveness with no safety. Just make all the lights green, always. Without, then it's fine, but of course the safety is not satisfied. The trick is to have both of them, okay? So any real system, all the properties are always a combination of those two, okay? So, to be very precise, a property, P, is a function of an execution, okay? So I have an execution, E, which is a sequence of configurations with events, okay? E1, E2, E3, goes forever. The property that I'm going to talk about is a property, a function that takes an execution, a whole execution, this infinite thing, as an argument, and returns true or false. A function that returns true or false is also called a predicate. Okay, so it's a predicate on an execution, which is a big thing, huh? So we're looking at whole executions here, and you can prove formally, and this was proved in a very famous paper in 1985, any property of the system, any at all, can be expressed as the conjunction, so the and, of a safety and a liveness. So no matter how you define the system, it's always a safety and a liveness. That is a formal result. You give me a property, I can show you that this is a form of safety and a liveness, always. Okay? So it's enough, we can define our systems in terms of safety and liveness. We don't have to do anything else. Safety and liveness are enough. Okay? Now let's make some formal definitions here. So we're talking about executions. Execution is a big thing. So let's try to break it down. I will define the prefix of an execution, or a prefix of an execution is the first part. So if I have an execution with many ck plus 1, ck minus 1. So a prefix is the first part of execution, is the first k configurations with the events. Let me maybe make this a little bit nicer. So C0, C1, C2, ck minus 1, ck, etc. D1, D2, D3, up until dk minus 1. So this, going from C0 to ck minus 1, this is a prefix. It's a prefix with k configurations. Of course, k can be anything. We can have small prefix, big prefix. This is a prefix. Okay? An example of a prefix. Basically, you cut off the tail. It's actually very intuitive. It's the first part of the execution. Starting from initial configuration up to some configuration and then nothing. Including the events that you needed to get there. So that's a prefix. And now let's go from a prefix, we can make an execution. So we can take this prefix and we can keep going. So any execution that has P as a prefix is called an extension. So this execution is an extension of the prefix, okay, of P. So let's call this prefix P. So this execution is an extension of P. The whole execution. So any execution that starts with P is an extension of P. So it's like you start by doing this, and then you go on and do more stuff. So that's pretty intuitive, huh? So prefix and extension, it's very intuitive, okay? We're going to use this to define formally what safety and liveness mean. So we start the execution with some prefix, and then we keep going. And the full execution is called an extension of the prefix, okay? Now we can make a formal definition of safety. First of all, of safety. So I give you a formal and informal discussion with prefixes, and then we make a formula. So we have a property P of an execution. So a safety property, P is a safety property if every execution that violates P, so if P of P is false, so assuming that it violates, then there is a bad event in there. every execution that starts like the beginning of E, so it starts just like E, up to this bad event will always stay bad. So basically there's a bad event in there. Okay? Safety property is a bad event, if there's a bad event. So formally, given any execution E such that P of E is false, okay, so the property does not hold. It does not hold, then there exists a prefix such that every extension of that prefix is also false. That means like the system is broken. In that prefix, the system breaks, and nothing you can do can fix it. If that's the case, then it's a safety property. Safety means if it's broken, it stays broken. So, for example, there's many examples. If I take an egg and I drop it on the ground, splat, it breaks, and there's junk all over the ground. The egg is broken, okay? There's no way to fix it, okay? I don't know how to put the egg back together. The system is broken. And any execution, so anything with that egg, where the dropping of the egg is in there, no matter what I do after, the egg will stay broken, okay? So that's a safety property. There's always, the system, it goes bad somehow. So if I have an accident in a car, I crash the car into a tree, boom. After that, whatever I do, the car will be broken, okay? The system is broken. So a safety property is a property such that when the system goes bad, it will always stay bad, no matter what you do after that. That's the formal definition of it, okay? So here's an example. Here's a property of the distributed system. Point-to-point message. I send message from P1 to P2. Here's a property. A message sent is delivered at most once. So I'm sending a message and it arrives once. At most, or 0 times. It arrives 0 or 1 time. So this property is a safety property. So how can we break this? How can I do something that will break this property? That will make this property false? It's very easy actually, yeah? At most once. How can I break that? You tell me. Tell me, somebody. 0 or 1, but what if the message, what if it?
Failed.
Sorry?
Failed.
No, it's delivered. So it arrives 0 or once, according to this property. But what can I do that's not covered by this?
Message is delivered twice.
Twice. For example, I send a message, but somehow the same message is arriving twice. Well, that breaks this. Okay? It's like the message has been duplicated in the system. But there's no way to fix that. Once the message arrives twice, whatever I do after, any extension will also violate. There's no way to fix it, okay? I cannot undo that arriving twice. So that's a safety property. When you break it, it's broken. I mean, broken is broken, okay? So that's safety. Let's define liveness now. So safety basically means you break it, it stays broken. So let's talk about liveness, which is like nicer. A system is doing good things. So what does it mean again? Again, we can talk about it with prefixes. So we have an execution E. For every prefix of E, so let's say there's a prefix F of E, you can always make it true. So no matter how you start executing, you go up to some point, then maybe the property is still false here, maybe it's still false, but there's always a way to make it true. there exists an extension of P for which P is true. So you can always make it true. So you can somehow say, as long as there is life, there is hope. That means as long as you're executing, you can always make it true in the future. There's always a way to make it true, which is like saying there's hope, okay? So that's a liveness property. So here's an example of a liveness property. So again, let's talk at this point to point. A message sent is delivered at least once. That means maybe the message is duplicated. It's coming in once or twice or three, but at least once, so not zero. So why is this liveness? Well, let's say I do my execution up to a certain point, prefix. And the message has not yet been delivered, okay, in the prefix. And then I want to extend the prefix. Well, I can always deliver later, and then it becomes true. So there's always a way to make it true, okay? To make it true in the future. So here's more precise explanation. So take the prefix, or any prefix of an execution. If the prefix contains delivery, then we're fine. It's already at least once. We're done. And any extension, it'll always be at least once. Maybe more, but at least once. And if the prefix doesn't contain the delivery, well, you can always extend it. There's always a way to extend it. You just put in a delivery in that extension so that it contains the delivery. Prefix plus the extended part satisfies P. Okay? So there's always a way to make it true in the future. If it's not true now, you can always make it true. So that's a liveness property. You can always make it true. So here is this diagram. For me, I kind of like this. You may or may not like this. Your mileage may vary on this diagram. Here I summarize it as a picture. So I'm a very visual person. Maybe you're more like formula person, I don't know. But this is another way of looking at it. So here we have an execution E, which is this green arrow. So a safety property means that there exists a prefix such that all extensions are false. So in this prefix, we're sort of breaking the system, and there's no way to fix it. If this is true, it's a safety property. Liveness is like a dual, different way of looking at it. Here's my execution. If we take any prefix, no matter which, we can take any prefix here, and there's always at least one extension that makes it true. You can always find an extension to make it true. You can always do something that makes it true. Okay? So this is safety, this is liveness. So with this diagram, you can kind of see that they're very dual properties. They're very complementary. I like this diagram. You may or may not like this diagram. I know some people, they like this way of looking at it. Other people, they think this is very weird. Up to you. You can use this if you think it's okay. Okay? Some more intuitions, and then you will actually be using it a lot in this course. Huh? Intuitions on safety. Safety can only be satisfied in infinite time. That means you can always break the system. While it's running, you're never safe until the whole thing is done. Okay, you're never really safe until the whole thing is done. And when it's violated in finite time. So there's always a prefix that breaks the system, which is a finite time. So you can only satisfy safety after you look at the whole execution. You're never really safe until it's all done, okay? It's only done when it's done. This is safety. And when the system breaks, it breaks in finite time. So never, at most, cannot, partial correctness. So these words are all safety words. Okay? Some intuition on safety. So liveness is just like the opposite. Liveness can only be satisfied in finite time. It means the good thing will eventually happen. Some good thing happens, but it happens in finite time. So it's satisfied. But the only way to violate liveness is to look at the whole execution. If you look at the whole execution and nothing good happened during the whole thing, infinite, then it's violated. Okay? It can only be violated in infinite time, but when you satisfy it, it's a finite time. So eventually, it must at least, termination is a liveness property. The algorithm terminates. That's liveness property. Okay? So you see, I'm trying to give you intuition, but also formal definitions. Okay? And we're going to use this everywhere in the whole course. So some questions for you to think about. So here's a question. So I've defined safety, which is a property, this is a safety property, true of an execution. It's true, it's a property of an execution. Why not I do like this? Why don't I do another way? Here's another way of defining it. For all configurations, in the execution, I have a property that's true of all configurations. Why don't I define safety to be true of configurations? Why do I define it as a property of the whole execution? Now here I have an execution. Execution is this big infinite sequence. So why don't I do something simpler? Why don't I just say safety is a property of the configuration. This is a safe configuration. This is a safe one. This is safe. Why don't I just do safety in terms of configurations? And not for the whole execution. And there are some books, older books, that do like that. They say, let's define safety to be a property of configurations and not executions. Actually, this is not so good. This way of doing it is very limited somehow. There's problems with this. So why is defining safety as property of an execution better, much better, this is like really the nice way, than defining it as a property of a configuration? Seems intuitive, right? I have the system, it's in a configuration. This is a safe configuration. Or this configuration is not safe. Yeah, seems kind of nice, right? But actually it's not so nice. Why not? This is a very subtle kind of question. One way to think about it is I can give you a very simple property. Okay? Notice. I can give you a very simple property, a safety property, that you can define in this first way very easily. And it's very obvious, it's very simple, very nice, but you cannot define it in the second way. So, very simple property. Really, really simple. As simple as some of these guys. As something like this, but very simple, slightly different. And you can define it with P of an execution, but you cannot define it if you just look at configurations. In fact, a single configuration is like a snapshot. What if you need a property that is more than that? What if that property, you cannot tell if it's true or not by looking just at a snapshot? What if you need to look at the evolution of the system to see that it's true? Can you imagine a property like that? I can tell you a real simple property, so simple that you can define with this, but you cannot define it here. A simple property, yeah?
Maybe, let's say we have something like a coin or something that's flipped.
Yeah.
And the the violation of the property to not be violated is the coin to be heads twice, for example.
That's a good example. That's a very good example. So the property is the coin will never be twice heads in a row, or something like that, or whatever. But if you look at a single configuration, you cannot tell, because it's only showing you one head. So what happened before? You don't know. So that property cannot be defined in this way. So in a distributed system, you could do something very similar, like the message, a message sent is delivered at most twice. That's a property. But if you look at a single configuration, well, okay, so let's say the configuration, the message is delivered, you don't know how many times. If you look at one configuration, if you look at the whole execution, you can see it's delivered here, and it's delivered here, and it's delivered here. The whole execution gives you the whole time evolution of the system. So if the property is the message is delivered at most twice, you cannot define it as a property of configuration. You see that? But you can if it's an execution. Because the execution shows you all of the places where the message is delivered. And if there's 3, it's broken, okay? Whereas this configuration will only show you maybe 1. Will only show you 1 delivered. You don't know if it's been delivered more than once. See that? Snapshot is not enough. You need to have a property that shows the evolution of the system. Okay? So that's kind of subtle, huh? So this question kind of forces you to think really what it means, this property. Yeah? I mean, it's easy to memorize this and to say, yeah, it's like this. But why is it like that? Okay? Why not like this? Intuitively, why not? Okay, but there's good reason why not. Okay? So that's one thing. So you can think about this still a little bit by yourself. Huh? Try to understand that. Here's the second question. So I told you before that every property is, all you need is safety and liveness. You can take every property and have it be a safety and a liveness property. Okay? So here's a property. Every message should be delivered exactly 1 time. Exactly once. So that's not a safety and that's not a liveness property. Or what is it? I mean, at most once is a liveness, at least once is at most once is safety, at least once is liveness. What's this? What is this one? Liveness, safety, what is it? You tell me. Exactly once. So I told you, if it's at most once, every message is delivered at most once, you can break it by delivering it twice. So that's a safety property. Every message is delivered at least once, that's liveness, because you can always make it true in the future. What about this? What is it? Actually, the answer is very simple, but you have to understand safety, a little bit safety and liveness. Okay? So think about it. What is it? What is this? Yeah?
Maybe a combination of both. So it's liveness that eventually it will be delivered.
Yes.
And safety that it will never be delivered.
Yes. So you're saying it's a combination of both. That's exactly right. This is a conjunction. This is a safety and a liveness. And what I said to you before was that any property can be written as a safety and a liveness property. So this one is a combination. It's a safety and a liveness. Okay? So it's at most once and at least once, with an and in between. So at least once is liveness, at most once is safety. And this is the conjunction of those two. So this follows exactly what I said in the beginning. Any property, So this one is not by itself safety or liveness, but it's a combination of both. Okay? Very good. Yeah.
Sorry, can you
Yeah.
repeat the liveness and safety?
So this message is a combination of a safety and a liveness. It's saying every message is delivered at most once. That's a safety, because you deliver it twice, you break. Every message delivered at least once, that's a liveness, because if it's not delivered, you just deliver it later, and it makes it true. So at most and at least together makes exactly once. Okay? So that's always true. Any property, so this property, so I'm trying to mess with your minds a little bit here. Right? So this property is a conjunction of both. And you can always do that. It's always possible. And it's very nice to do like that, because it makes it very clean. You could always write it as safety, properties, and liveness. You can keep them separate. Okay? So it's every message should be delivered exactly once. Okay? So here is, so now I want to talk about failure, but just one little thing, let me jump a little bit ahead now, and let me just show you another example of safety and liveness, and then we'll stop there. Right? So here, we're going to start writing messages going between two nodes. So if I have a message going from one node to another node, and there's some link here. Here I have a node, P1, P2, and the connection is a link. So a fair loss link is that the message will be delivered with non-zero probability. It means I send a message, it will be delivered maybe 50% or 30%. Sometimes the messages are lost. So this is what's called a fair loss link. Okay, and then there's other ones. So this is where the channel can sometimes drop the message. So a fair loss link, so it sort of looks like this, okay? So here I have two nodes and they're communicating. So I send a message and it arrives, but not always. It arrives with some probability. Sometimes it's lost, okay? So this is called fair loss point to point. That's what it is. Okay, so this is just to show you, but I'm going to define the properties of this. So it's going from two nodes. A message is going from two nodes, Pi to Pj. So we have Pi and Pj, okay? And there's a link between them, and we send a message. So the fair loss link has three properties. This is the specification of it. So I'm going to explain it to you, and then we'll see how this fits with safety and liveness. So this is a nice exercise. Huh? So the first property is called fair loss. If the message M is sent infinitely often by Pi to Pj, and neither of those two is crashing, then it will be delivered infinitely often. This is how we talk about the probabilities, okay? So if you keep sending the message without stopping, it will keep arriving. So if you send infinitely often the message, it arrives also infinitely often. It's not like if you send the message infinitely often, it only arrives 3 times. No, it just keeps arriving. Maybe it arrives slower, a lot slower, but still it arrives infinitely often. Okay, so that property is called fair loss. So it's not enough. There's also this, fair loss has this second property called finite duplication. If you send the message a finite number of times, it's only delivered a finite number of times. That means the message will not be duplicated infinitely. That you send in a message, one message, and then infinitely many come arriving, boom, 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 boom. No. This is kind of an unreliable network. It's like internet. I send a message, and maybe it arrives, but the same message might arrive twice, because maybe there's a problem with the router in the middle, So it sends there, and then it thinks this other router has crashed, so it tries another one, but this one actually didn't crash, so the message can arrive twice. So it's possible for a message to be duplicated in a real, like IP, UDP IP connection, but only finite number of times. If I send a message once here, maybe it arrives twice or 3 times, but not infinite. So if M is sent finite number of times, it's delivered finite number of times. So that's another thing. And the third property is no creation. That means if I don't send a message, nothing will arrive. This network is not going to create random new messages. No message is delivered unless it was actually sent. So the network is not going to create messages. Okay? So these 3 properties define like IP in a very formal, very precise way. Now the question is, FL1, is this safety or liveness? Now I'm asking you, it's an exercise. Is FL1 a safety or a liveness property? Think about what it means. A safety property means that you can break the system by dropping an A, and you can never fix it after. Okay? A liveness property means the only way to break it is to look infinitely long. As long as there's life, there's hope. Okay? So a liveness property, a safety property, can only be satisfied if you look at the whole execution. The liveness property, let me show you, no, let me go back to the intuition here. So, safety can only be satisfied in infinite time. You're never safe. It can only be violated in finite time. Liveness can only be satisfied. It can be satisfied in finite time, but it can only be violated in infinite time. So, if something goes wrong, then it's infinite. So, this is actually, maybe I shouldn't have presented this because it's a little bit subtle, but well, what the heck? Okay, these are not the simplest ones, okay? How can you violate this one? What does it mean to violate this property? What does it mean? To not do that, to not satisfy this. You send infinitely often, and you deliver infinitely often. So violating means you send infinitely often, but it's not delivered infinitely often. It's only delivered a finite number of times. Okay? But how can you know that? How can you know that it's delivered finite number of times? The only way to know that is to look at the whole execution, right? Because if you look at part of the execution, of course it's going to be finite, but maybe more is coming after. The only way to be sure that it's delivered finitely often during the whole execution is to look at the whole execution infinitely long. So the only way to violate this property is to look at the whole execution. So what does that mean in terms of safety and liveness? You tell me. Maybe we talk about it. Maybe I let you meditate on this. Okay? Let's do this one, which is easier. No message is delivered unless it was sent. How do you violate this one? Well, the system will create a message, some weird message, MX, and send it there, even though nobody ever sent it. Some random new message just appears miraculously and gets delivered there. So what does that mean? Is this safety or liveness? FL3. If you do that, what has happened? You have dropped the egg, right? You broke the system, right? You broke the system here. If this happens once, the system is broken. So this is a safety property, okay? This others are a little bit hard. Maybe I should have not shown this example as the first example. Maybe we forget that I presented those. We'll talk about them next time, okay? I don't want to. These you have to actually, as you were talking about, this whole reasoning, infinite and finite, it's a little bit subtle. So I propose that we go back to that next time, okay? Okay, so I think we can stop here. So I hope this kind of gives you some understanding what safety liveness. Go back and look at the formal definition, look at the intuitions, look at this, think about this, think about these things, make sure you understand it.